Thanks everyone. So I'm CTO at Craftinity. I'm a machine learning engineer. And today I'm going to talk about explaining neural networks prediction and interpreting machine learning models. So before we start, if anyone wants to have slides already before the presentation on laptop, you can go to my GitHub, Plażowicz with Z and DataSphere 2018. Yeah, so before we start, there's a question. So you can choose between AI doctor, who is 80% accurate, and can explain his diagnosis, and with AI doctor, who is 90% accurate, but cannot. Which one do you choose? So for the first one, raise your hand. Yeah, for the second? I think second wins. Okay, we'll see what's going to happen after presentation. Yeah, but can explain why. So that's a good reason. Okay, so at the beginning, why do we need explanations about trusting in model and machine learning algorithm LIME to generate explanations on predictions? So machine learning is everywhere. NVIDIA CEO said that software is eating the world, but AI is going to eat the software. Probably it's not going to happen this year, next year, but definitely I wouldn't say that there is going to be next AI winter. And you can see it everywhere. So you use probably Netflix, and there are recommendations. In Spotify, there's this discovery mode, which works pretty well. On iPhones, we have Siri, self-driving cars, and so on. And here, there's an example from our demo from our site. So if you have time, you can go to lookbot.craftinity.com to see how to find similar clothings on the images. Yeah, so how do we train machine learning algorithm? So we need data, usually, so the data contains of some samples and targets. So we have answers and actually what we want to predict. In case of supervised learning, we have some machine learning algorithm. We train this. So we have this phase for learning, and then we can deploy, let's say, as a REST API, and we can, our application can ask for predictions. For example, if there is some dog on the image. So let's look at the example. So we want to predict if there are football shoes on an image. So we have some data set with images, so like with Robert Lewandowski or some other players like Henry, and also some other celebrities like Eva Longoria and Brad Pitt. And we have already trained shoes detector like Faster RCNN or YOLO, so we do only classification on those cutouts, on those bounding boxes. So typical process is we divide our data set into training set, validation set, and test set. Define how we can measure this performance. Let's assume that our data set is uniform with respect to labels, so we can use just accuracy. We choose some state-of-the-art architecture. My favorite one is ResNet 50 in Café, so let's take this. And we train this on train set, tune some hyperparameters like doing early stopping, for example, on validation set. And then we can evaluate this on test set. So we get 95% accuracy. So it's pretty good, like for 1 hour of training, fine-tuning this model. So do you trust this classifier? So if someone trusts, maybe raise hand. I know this is a tricky question, but yeah, so could you repeat? Yeah, just you lose that you have, yeah, just a toy example, and you can't lose like life, probably. Fortunately, if we are wrong, with our toy examples, we don't lose lives. So always a good idea to do eyeballing, so visualizing our predictions. So here we have football shoes, not football shoes, like in the Silicon Valley TV show, not hot dog. Football shoes, not football shoes. Looks really great. Here we have football shoes. Whoops. That doesn't look like football shoes actually. Let's look at more examples. Yeah, this one is quite similar still, but it's from golf pitch, from Eva Longoria still. And here are definitely not football shoes. So something is bad. Yeah, what's going on? So does anyone have intuition? What's wrong here? Yeah, exactly. Our classifier learned to recognize grass, not actually shoes. Yeah, so this is also a classic Kaggle pitfall when we have different distribution between the test set, the real test set, and the test validation set. And it's a good idea to use something called adversarial validation. You can learn more here. Yeah, but basically the idea is that distribution of a training set and the real data test set are different, and we can check it. Training classifier, when we label the training, we need to train classifier to differentiate, to distinguish examples from the training set and the test set. So if they are very similar, this classifier should have accuracy around 50%. And this is okay for us because we're training on similar images. But if actually the test images are much different, or test examples, because it can be anything, then it's a good idea to choose examples to validation set that are in cross-validation mode for training set that are most certainly predicted as the test set examples. Yeah, so we had this learn model and deploy model pipeline, but probably it's a good idea to add something like trust model, explaining why those predictions are like here. At example before, we had quite simple intuition with grass, but not every example is so simple. Not always is easy to explain those models. Could be a good idea to try. So how we can gain trust? So one thing are interpretable models. So for example, shallow decision trees are quite easy to interpret for humans, but if they are really deep, it's not easy. So it's not gonna work. But the problem with shallow decision trees is they are much worse in case of many tasks than, for example, deep learning. Yeah, so the other thing is accuracy, but as you can see already, that accuracy can lie if the real data distribution is much different than our training data. And in many cases, we actually don't know the real data distribution. So accuracy probably is not enough. Good idea is A/B testing. So we actually have some model in production, we deploy the other one, put some users on the other one, and we can compare those models, like how they actually perform on real data. But it can be expensive, and we can expose really bad, shitty model to our users. So there is a trade-off. The last thing is voodoo. So we have those machine learning engineers who did that stuff a lot of times, and they just know that something's gonna work or not. Those are people you want to hire. But maybe we can try to explain individual predictions. It's hard to explain whole model because we would need to understand this model globally, but local predictions needs only local understanding. And the good thing about most of the machine learning models is that locally you can approximate them with linear functions. So we have 3 must-haves for good explanation. The first one is that human is able to interpret those explanations. So in case of shallow tree, this is example from the Titanic data set. So basically, if a person was female, then survive. If a man, then we check age, then we check how many siblings, and finally we have die or live. But with deep decision trees, it's not so easy for human. Probably it takes a lot of time and really good memory. Yeah. So the next thing, it's is model faithful. So So the model for explanations needs to describe actually our model quite good. So the problem globally with linear models is like if we have nonlinear functions, they don't fit nonlinear functions. But just in some surroundings, we can approximate with linear functions. So the whole idea is to do this locally to make those models for explanations faithful. And the last thing is model agnostic. So we would like to have one algorithm to explain deep neural networks, random forests, support vector machines, and so on. And there is thing called, yeah, good luck with that. Yeah, but there is something from 2016 called local interpretable model agnostic explanations, shortly LIME. And it works quite well. And it's quite easy to use, so we can take a look at it. So there are two key ideas behind LIME. So we have this example. This is binary case of classification. So the blue one surface is for some class and the other surface is some for other. We have some example. So the first idea behind LIME is we pick a model which is interpretable by humans. So for example, linear regression, and we have linear decision boundary. And it's very easy to understand that this line is actually very good to distinguish which example belongs to which class. So we are approximating this black box model because predictions could be from deep neural network, from anything. So we don't think actually about some specific algorithm, just black box machine learning model. And globally is very bad, but locally is good. Yeah, so how it works. So we sample a couple of points around our point. Yeah, the one important thing, this LIME thing, it's also machine learning algorithm to explain machine learning algorithms. So probably I say a lot of times model, and I could reflect one or the another one. So I will try to say LIME when I'm saying when I'm talking about this specific model. So we sample some points around our example, and we predict labels with our complex model. So for example, deep neural network. We weight those samples according to distance to the example with some kernel. They use, I think, some exponential kernels. And we learn linear regression and exactly k-lasso regression on those samples. And then when we learn this model, we can provide some explanation. And right now it can be probably vague. So let's go to, yeah, those are negatives, those are positives. Yeah, we sample positives and negatives, more positives probably, but both classes. So let's go into example how it really works. So let's take example from images. So we have this nice image with that we can predict here that there is a Labrador, and probably we can predict even that there is human and guitar. So the first thing we do is we do superpixel segmentation. So this is just clustering, and we have some number of those superpixels that can be ordered in some arbitrary way. So on the original image, we have probability of Labrador 0.21, and we sample neighborhood images by randomly covering some superpixels of the image. So we just randomly cover those superpixels to get a new image, which is, let's say, quite similar to the previous one. So on this image we have high probability for Labrador. Here the face of dog is not visible, so we have really low. Yeah, and we have, like, let's say 1000 those examples. And then we do linear regression. And then we can predict on the input image. So basically linear regression learns some weights. And k-lasso regression especially learns those weights in the way that it shrinks some weights to zero that are not important. So it shrinks weights for superpixels that are not important for this image to zero. So once we learned, we just take the weights which are high, and we show only parts of the image which were important for our k-lasso regression. So the weights are quite high, and this way we can see which parts of the image were the most important for our prediction. So for Labrador was obviously face, and probably I have no idea why this part. Yeah. So this way we can explain very easily predictions from Inception v3 or any other network, but this is just example. So if you go to the Lime project page, there's notebooks with examples, and they're pretty well explained. So we can easily run some explanations from Keras or from random forests with Lime. So here are some explanations for electric guitar, which actually makes sense that it's 0.32, because the most important part is we don't see this part which is specific for acoustic guitar. So for acoustic guitar we have 0.24, and for Labrador we have the same as before. Yeah, so another task. So we want to predict wolf or husky. Yeah, so we have a classifier, and yeah, here is wolf, and predicted wolf, and it was wolf, so it's okay. Husky the same. Yeah, actually we have only one mistake. We have here a prediction that it's wolf, and actually it's husky. So do you trust this classifier? Yeah, I thought so. Yeah, so does anyone have intuition why it's predicted as a wolf? Snow, yeah, exactly. So when we visualize predictions with Lime, then we can see that whenever we have wolf, we have actually the most important part was snow. Yeah, so probably it's not a good idea to not explain sometimes those predictions, but just in the minute. So explanation should match our intuition. So we have wolf with original image, and snow is bad, but the actual part of wolf is good. And if we don't have such good classifier, wrong things can happen. Yeah, because you can end up buying a wolf. Yeah, so if you want to learn more, here is the site of project Lime. We can just install with pip and very easily use. Just look at the examples in notebooks, and it's quite easy to use. The other interesting stuff in the interpretability of machine learning models was done recently by Christopher Olaf from Google, but it was only for convolutional neural nets. And just like 2-3 weeks ago, the authors of Lime introduced a new project called Anchors, which is not really finished, I think, but they claim that it's better, so it's probably worth checking. Yeah, so most of the credits for this work is to those guys, Marco Tullio Ribeiro, and yeah, you can read this probably alone. Yeah, so they publish a paper. Why should I trust you? And explaining predictions from classifiers. Yeah, so they have really great talks on YouTube, and of course they introduced this project Lime, which is really easy to use. And actually in Craftinity we're starting to work on CT scans and abnormal lymph nodes detection. And in case of medicine, probably explaining predictions of deep neural networks could be important. I would choose this 90%, of course, AI doctor, but probably because of some legal stuff, it has to be explained sometimes. Yeah, so does anything change? So who is for 80% accurate explanation? Yeah, I think it's similar. Who is for 90? I think it's less. But it's like voting 100 years ago in US in Congress. Yeah, so actually the question is from Twitter, from Pedro Dominguez, who wrote Master Algorithm, who is professor of machine learning, I think in Washington, but no, in Seattle. Yeah, so he would choose the 90%, basically. Yeah, but a lot of people who conversated on Twitter with him chose the first one. Yeah, but at the end, this is important quote from Mark Twain, because as a machine learning engineers, we should be careful to not trust too much model and probably our skills, because the thing you know for sure, it's going to hurt you at the end probably, if it's not so sure. Yeah, so if you have any questions, I'll be happy to answer. Thanks.
Thank you, Matthew. It was great, inspiring talk. Any questions? Okay, okay. You wave quite ambitiously, so I'm coming to you first.
Yes, I have two questions, please. First of all, can you please show us again the slide with the Husky classifier?
Yeah, sure.
Where the background was highlighted?
Yeah?
Yeah, this one. So just as with the example with football shoes,
yeah.
The classifier learned to recognize some background in which wolves happens to be right, but we humans know that it's not necessary for the wolf to be in this background, so maybe we can help. We can, first of all, we can detect objects, any objects, right?
Yeah.
And then just remove the background, eliminate, gray it out, green it out, so that it will be the same on every training sample. And in this way, we will force the classifier to actually learn to recognize object, not the background.
Yeah, that's kind of true. The thing is, like, gathering annotations for actually bounding boxes is more time consuming than just for a classification. The other thing, probably we would fix the thing with snow and grass, but it could happen that there are some, you know, like maybe some facial features that actually matter. It's hard to say, but yeah, for grass and for snow, for just background detection should help.
Okay, thank you. And the second question, can you please return to the slide where there was a complex area, white and blue, and a simple line
Yeah.
boundary fitted to explain the model?
Yeah.
Yeah, this one. So, as far as I understand, there is the neural network derived some set of complex rules to get the actual boundary of the two classes, and
Yeah.
in order to explain this complex rule in some local area, a simple model was fit. And I don't understand what is the use of this model if we know for sure that it is generally wrong. It happens to coincide with the right model in a single small area, but generally it is wrong. I don't understand what is the purpose of this simple model.
The purpose of this simple model is just to explain this one prediction. I mean, we can run this simple model for each prediction. It's quite fast, so probably on GPU it should be less than a second, I think. So we can explain a lot of predictions just locally. Of course, we don't understand the model globally. There is some research done in this area about understanding also models globally. Yeah, but sometimes those, you know, like the predict. If you want to, oh, there is a great example with Netflix. Netflix actually had better machine learning model with higher some precision score for recommendations, but finally they used the one with lower that was more easily explainable because it occurred that people found the recommendations better when they had explanation why they should actually watch it. So in this Netflix case, it would really work.
Okay, but in as far as I understood, in this case of Netflix, the classifier that the network that they chose, gave a less precise gave explanation that were sometimes wrong, but at least it was confident that they were correct everywhere. And in this case, we just it And in this case, we just give a plausible explanation, but we know that it is wrong. It's not actually an explanation, it's an excuse.
Not necessarily we know why it's wrong, because we, like if we go to the Husky example, maybe, yeah, so we know that prediction is wrong. Yeah, maybe we know that the prediction is wrong, but we don't know why. And explanation is we want why the prediction is wrong. So because the other important thing why we need explanations is so if we understand the models which are bad, we can improve them. So once we understand in this example, because of using the slime algorithm, that the snow is a problem, then we can figure out, as you figure out, that we can do detection, so there is no background, and it should work better.
This fitting of more simple models is generally useful for detecting causes of mistakes, right?
Yeah.
Okay, thank you for the explanation.
Thanks.
Okay, thank you for the questions. We have one more question, and then we will go for a lunch break.
Okay, so could you go to the slides with the Labrador where you split the picture into what you call super pixels?
This one?
No,
before.
Yes.
Yeah.
Could you elaborate on how those super pixels are chosen? Is it some clustering? Or?
Yeah, I think it's quick shift clustering on this example.
Okay.
But I'm not sure. But it's generally clustering on color space.
Okay, I see. Thanks.
Perfect. Thank you very much for the questions. Thanks again, Matthew, for the great talk. So guys, we have a lunch break. We're going to start at 2.